Okay, so I talked about overhead, then let's look into this overhead. The question is, what kind of overhead do we have in the system? And this is manifold, right? So we have once the overhead that comes by the encoding vector. This depends on the generation size, on the field size, and on the payload. And therefore, the number of additional bits for each packet is only G multiplied logarithmic 2 field size if you use full RLNC, right? That can be smaller if you have it sparse, if you can compress it, or if you use the perpetual. There you can deal with it. This is the maximum, right, that can happen to you. But you can do this. The other overhead comes from linear dependent retransmissions. So in case you try to be super smart and make it too sparse, you may end up with something, say, yeah, I'm sorry, but you have to repeat the packet. Or if you think you can reduce the encoding vector by using a binary field, which decrease the encoding vector, but then you have the 1.6 packets extra. This is also overhead. So these things belong to each other. Now, here's a nice plot which shows the linear dependency for different density levels and fields. On the y-axis, you see linear dependency, overhead in percentage, and here's the generation size. And the dashed lines are the binary field. The solid lines are the binary field, and the dashed lines are the higher fields. And then you have a density, right? So this one here, the solid line is binary and density 1/2. If you now this one is 1/4, this is 1/8, 1/16. If the generation size is very big, they all end up in the same curve here. But if the generation size is small, then it matters. Okay? Then the overhead goes up. The same for the higher fields. They are different for smaller generations, but they all end up for higher generations. Also nice that they more or less start the same way, right? This is with the same density, for example, 1/16, and the higher field and the small field are actually the same because it's so low density, but then if you increase the generation size, they are going apart, and then you have 2 orders of magnitude difference in the overhead. So this is the overhead from the linear dependency, by the way. So that I must say, right? It's not the overhead itself. Now, this is okay. There's some text for you in the slides. If you now look into this overhead in the total, so overhead by code efficiency, overhead that is introduced by sparsity, and overhead due to the encoding vector. This is a very nice plot here. The plot shows you the total overhead over the density. And the upper curve is what you really are interested in. But the areas tell you where it comes from. So this brownish down here, this is alpha. You cannot see it here on the slide maybe. These are additional transmission due to field size. So here we have a binary field, and this alpha is quite big. Higher fields, bing, it goes down. So the likelihood that you have to retransmit something, very low. Here it's quite high, okay? Here we have a generation size of 64. Here we generation size of 1024. The same generation we have here. Here is only the field size different, and here is the generation size different. And this is the code efficiency. Then this one, the orange one, the gamma, this is the impact of the encoding vector, which is very small when it comes to the binary field with a low generation size. It grows up a little bit if you have a huge generation size. So remember, G multiplied logarithmic 2 of the field size. But it becomes really huge when field size is high and the generation size is high. Then the overhead really comes from the encoding vector. Now, then also density plays a role, right? Now, if the density increase, the impact on the overhead is going down, right? It's always the same behavior. But you see also that here is a very interesting point where you bring it down because the more you go to the left, the more linear dependency you're introducing. You're making something good for the complexity, but the overhead is bad. Overhead will always tell you, yeah, maybe you should not do it. But look now at the density where the optimal point is. Where between these two, they are more or less in the same area. Here, we have a 1 order of magnitude different density requirements. So the amount of density depends now on the combination of field size and also generation size. Okay, I made a little bit bigger for you that you can see it. Really, this was the additional transmission due to field size, additional packets due to linear dependency, and bits due to the encoding vector. And here, because it was binary and a small generation, very little overhead by the encoding vector. Okay? And these are the others, just that you have a better view on them, right? But interesting is how really the optimal density point is changing for different scenarios. I think with that, for today, I would call it a day, because the next stuff that we're doing is a little bit more complicated, has to do with the real implementation features of network coding. Because what you will learn next time is when we have the same packets, like packet 1, packet 2, packet 3, they're all, let's say, 1,500 bytes, everything is fine. But what would happen if you have packets of different sizes, right? The coded packets will always have more or less the size of the longest packet. How can we deal with heterogeneous packet sizes? This is something we would like to do tomorrow. And then we also will maybe bring you a little bit more of these examples. But for today, I would say thank you very much.